Welcome again in this advanced conduction series. So let us make a brief recall about what we did in the last lecture. So in the last lecture we have derived the thermal energy balance equation, but in the thermal energy balance equation, in one term, that is in the first term, we have something that is a function of temperature, and we can see that here the variable temperature is there, okay. But in the second term, this is a function of the function of temperature, but we don't know that function, that what should be that function in terms of the temperature. And the third function is the volumetric heat generation, and I told you that that is either given or you have to model that as per your practical problem, okay. Now I told you in the last lecture that in this lecture I will be talking about the Fourier's law of heat conduction, and I also will be showing that how that boils down to Q equals to minus Ka grad T, and here the K will be a constant for only an isotropic material, and I promised you that I will prove that. But before that, I thought that some of you, or maybe most of you, have gone through this derivation of the heat conduction equation, okay, and that is nothing but this equation only. And maybe in your undergraduate heat transfer course, maybe some teacher has taught you that thing, or you have gone through a classical heat transfer undergraduate textbook like Senzel or any other good heat transfer textbook, and maybe you have seen the derivation of the heat conduction equation, okay. And there most of the books, they use a control volume approach, okay. So I thought that uh, I should show the correlation between that approach and this approach, and I should show you that uh, both the approaches lead to a same result, okay. So let me derive this thermal conduction equation from the second approach, but this time I will do it a bit quickly, as I suppose that you have already done this. But still, if you face any problem, because I will be do it a bit faster, then you can put your doubt in the comment box. I will solve that. So let me first draw the, okay, before everything let me put the lecture number. So this is lecture 4, okay. Now I will draw the coordinate axis here. So this is my coordinate axis. So this is x, this is y, and this is z. So for a Cartesian coordinate, we generally take the control volume as a cube, right? Okay, so the cube has converted to a circle. So let me draw it like a, let me draw it by straight lines only. Okay. So this is the cube, and this is our control volume, and this cube is having side lengths as delta x, delta z, and in this direction the side length is, you can guess, that is delta y, okay. So considering only in x direction, so x direction heat transfer, okay, we will get that, you see that from this face, q dot x, amount of rate of heat transfer is there, and from this phase okay, the rate of heat transfer is q dot x plus delta x. Okay, and I have my uniform volumetric heat generation rate as q triple prime. Therefore, total volumetric heat generation in this control volume is q triple prime into the volume, that is delta x, delta y, delta z. Clear? So, if I write the energy balance equation for this control volume, then I will get q dot x amount of heat is entering per unit time plus some heat is generated inside the control volume and minus minus some heat is leaving the control volume per unit time, and that will be the total change in internal energy. And if I consider it to be a solid, then I know that Cp equal to Cv. I proved this. So, this will be rho C delta T, and obviously volume, because rho into volume is the mass, and that will be the internal energy change, that is mc del T del T. This is time, this small t is time. Okay. Now, if I write the expression for all the terms which I know, so this plus this will be q triple prime into the volume delta x, delta y and delta z, that will be equal to rho c delta x, delta y, delta z into del T del T. Okay. And now you see that if I now, what can I do? I can divide the whole thing by delta x, and I can write this as qx plus delta x minus qx. In that case I have to take a minus out and it will be by delta x. Okay, plus q triple prime delta y delta z, okay, is equal to rho c delta y delta z into del T del T. Okay. Okay. So, now if I put a limit, that is limit delta x tends to 0, and it will be taken on this thing, okay, taken on this first expression. There are some extra brackets. Okay, now it is okay. And also in the second expression and third. So, second and third expression, that is these expressions are not having delta x. So, let me, and so this will remain same, that is q triple prime delta y delta z, right. So, that is okay, fine. Now, this we can recognize from the definition of derivative according to the first principle, that is this is equal to minus of d qx dx plus q triple prime delta y delta x is equal to rho c delta y delta x. Okay. Now, I can write this qx as, I can write this qx as qx double prime, that is the component of the heat flux vector in the x direction, into cross sectional area that is normal to the heat flow in the x direction, okay, or cross sectional area normal to x direction, okay, plus q triple prime. So this will be the same expression, so let me just copy it and paste it. Okay. So now you see from this diagram, this is my Ax, this area, or you can say this area, this is my Ax, and that is equal to nothing but delta y into delta z, right? So if that is so, then we can recognize that this is nothing but Ax. So for Cartesian coordinate, this is this is not a function of x, okay. So I can take this Ax out, this Ax I can take this out, right. So Ax into minus del q dq double prime, actually I should write it as del, okay. So that will be mathematically more appropriate, because this can be a function of time also, okay. Okay, so and also Ax, so q triple prime into Ax is equal to rho c del t del small t into Ax. Now I can cancel this out, even if I take the limit. Now here actually I have to take the limit, that is delta x, delta y, delta z, everything is tending to 0, because I want to shrink the control volume into a point, then only it will be a differential equation, okay. So even if I take that limit, because the things are not exactly equal to 0, that is Ax is not exactly equal to 0, but it is tending to equal to 0, so that is why I can cancel out it, I can cancel out the Ax from the equations, from the LHS and from the RHS. So the equation boils down to what? Rho c del t plus del q double prime x del x minus q triple prime is equal to 0, okay. So this is valid for only x direction, okay, x direction heat transfer, okay. So if I want to write the y direction heat transfer, then what will happen? Then only one thing will change, and that is this term, this will be y and y. So this will be y direction, okay, y direction heat transfer equation, heat conduction equation. Similarly, you can write the z one. Now if you have to write in 3-dimensional, that is the most general case, then you will be having heat transfer from this phase also, that is for the y. So here you will have q y dot, and from this phase you will have q y plus delta y, right. And from the backward phase, okay, you will have q dot z, and from this front phase you will have q dot z plus delta z, okay. So you have to incorporate all these heat interactions from 3 directions, okay. So then for 3-dimensional case, the equation will be rho c del t plus del x of q double prime x, del y of q double prime y, del z of q double prime z, okay. and minus q triple prime is equal to 0. So if you recognize, then this is nothing but the divergence of the heat flux vector in Cartesian coordinate. Okay. So this equation and the equation that we derived from other approach, so both of them are actually same. Okay. Now let me tell you that if you change your coordinate system, then the expression for the divergence will change. Okay. So in that case, if you know or if you can memorize the expression for the divergence, then you can just replace this whenever you change your coordinate system. For spherical it will be different, for Cartesian it will be different, and for cylindrical it will be different. But you can derive each of those equations by taking this approach. Okay. So for a cylindrical coordinate system, so this will be your homework, and don't be afraid, I will again take all these derivations in the cylindrical and spherical coordinate when we will be taking those kind of problems for a cylinder and also for a sphere. But for the time being, I will just give you a hint by telling you that what should be the control volume for a cylindrical coordinate. So if this is my axis of the cylinder, okay, and so I can draw my cylinder here. Okay. Sorry. Okay, so this is not fitting. Let me draw it by freehand. Okay, it is done. So now your control volume will be like this. It will be a strip of a cylinder, elemental strip. Okay, so you can, okay, so like this and this. Okay, and I can draw a dotted line for the inner surface. Okay, and for the outer surface I will draw a solid line. Like this. Let me draw with another pen actually. Draw with this pen. This and this. Okay, and the inner cylinder I will draw with this one only, inner circle, and the outer circle I will draw by a solid line. Okay, so now my control volume is only this part. Okay, only I'm sorry, my control volume is only this part, this one, right? And the heat conduction direction you can take for only the simplicity case. Okay, you can take that my heat is only being conducted in the r direction, that is in the radial direction. So this is the r direction, this is the z direction, I mean along the this axis is z direction, and uh, if I draw the circular, if I draw the top view here, then for this circle, this is r, okay, and this is theta, okay. So r theta z, this is the cylindrical coordinate. So here you will consider that my heat is going through this, that is qr, and it is coming from this, that is qr plus delta r, okay, q dot obviously. So this thickness is delta r here, okay, and you have to consider the same analysis that I have done here. So this is your homework, and believe me, all these things will be useful to you in the upcoming exercises that we will do, okay. So now let me talk about the Fourier's law of heat conduction, okay. So Fourier's law of heat conduction. So Fourier was a great mathematician as well as an engineer, okay, and I think most of you have already heard about the Fourier series and the Fourier transform, which has got a great amount of application in engineering as well as in mathematics, in data science also, okay. So let us proceed with the Fourier's law of heat conduction. Let me tell you, no one can prove this law. I mean, no one can prove this law analytically, okay. Experimentally this can be proved and verified, okay. So before everything, uh, suppose that you have to convey this information that if there is temperature difference, there is heat flux. Do you have to do a great amount of work? I mean, is that a very difficult task? That is, you have to convey the fact to a layman that if I have the temperature difference, there will be the heat transfer, okay. So in the regional language, there is some terminology for heat. So you don't have to uh, put science or scientific facts or vector calculus or anything like that. You don't need any rocket science to say that if I have a hot steel ball here and the ice block here, then if I put them into contact, there will be the flow of heat, and uh, both of them will change their state, okay. Obviously, whatever I have told about this ice block and this steel ball, I have talked about some scientific terminologies like state, okay, heat flow, this kind of things. But without incorporating those scientific terminologies, you can tell that definitely my heat transfer rate, that is a function of gradient of temperature. Obviously, I have told this earlier in the lecture of the mechanism of conduction, that is, this heat transfer rate is not only the function of the gradient of temperature, but also it can be a function of the voltage difference, okay. But for the general case in our practical world, uh, what we experience generally, according to that, this is the case. So now I can write a Fourier series. So q dot is equal to, so sorry, not Fourier series. So this is, I am writing a Taylor series about 0. Now this will be del of q dot by del of gradient of t at gradient of t equal to 0 into gradient of t plus the second order derivative, second order term, and this will be delta square by 2, and this is also derived at delta t, grad t is equal to 0, plus the third order term grad T is equal to 0, grad T whole cube by 6, and so on. Okay. So now here we take an assumption, that is my grad T is very small, obviously less than 1. So grad T square or grad T to the power n is even smaller, okay, where n is greater than 1. Okay. So in that case I can neglect all these terms. Okay, so these are called higher order terms, I can neglect those. Okay, and from our daily life experience I can say that this is equal to 0 because there is no temperature difference. Then I can simply write Q dot is equal to del Q dot by del delta T at delta T is equal to 0 into delta T. Okay. Okay. So experimentally I have to find this quantity. Okay. So what type of experiment you can do? You can take a thermal energy reservoir here, okay, and another thermal energy reservoir here, okay, and in between that you can put a bar. So this bar is having a length, certain length, a particular cross sectional area. For the time being we take that this cross sectional area is constant, okay, and this reservoir is at a temperature Ta, okay, T small a because capital A is indicating area, and this T small b, okay, and you measure the heat flux here, okay. So now you can, I mean, you will be seeing that this thing. So now, I mean, in this experiment you directly put, instead of this grad T, Ta minus Tb, okay. So instead of this Ta minus Tb, instead of this Ta minus Tb, you directly put this, okay. So now from the experiment we can conclude, if you do the experiment, that this, or let me write for this experiment, that is del Q dot del of Ta minus Tb derived at Ta minus Tb equal to 0, okay, that is equal to, or that is proportional to the length, sorry, proportional to the area, and that is inversely proportional to the length, and therefore I can write this as Ka by L, where this K is the so called thermal conductivity, but for the time being it is just a constant of proportionality, okay. Now you see a very subtle fact, that is this function is evaluated at Ta minus Tb at equal to 0. So if Ta minus Tb is equal to 0, then the bar is at equilibrium, okay. So therefore this thing must be a property of the bar, okay. So this is a very subtle concept, that is, this is a property of the bar because this is evaluated at Ta minus Tb equal to 0, and if Ta minus Tb equal to 0, then my bar is at equilibrium, okay. Fine. So now therefore my Q dot is equal to Ka by L into Ta minus Tb. Okay, and my Q dot I can again write this as Ta minus Tb by L. Okay, and this is analogous to Ka grad T. Okay, and you see that if my temperature is decreasing, then this should be positive. That means if my grad T is negative, then this should be positive. So I would be writing a minus here. Okay, fine. I mean, I am writing this sign here, that is equivalent. Okay, just mind it. Therefore, my Q double dash in that direction only, that is minus K delta T. Okay. So if I write my heat flux vector, so therefore my heat flux vector, okay, is K into my temperature gradient. Okay. So now I am able to write this heat flux vector in terms of the temperature gradient. Now you say me that, you tell me one thing, that is, if I have a scalar phi, so phi is a scalar, then gradient of phi is a scalar or a vector? You just tell me that. If phi is a scalar, then gradient of phi is definitely a vector. Okay. So here the temperature is a scalar. That means this is a vector. Okay. So if I write this one in terms of matrix, this will be Qx, Qy, Qz. Okay. So now that will be, so I can satisfy if this K is a constant. So that is grad Tx, grad Ty, grad Tz. So here if my K is a constant, then also it is okay, right? But in general, if you have studied matrix, then this is a 3 cross 1 matrix, this is also a 3 cross 1 matrix. Okay. So if my K is a 3 cross 3 matrix, so can it be the case? So 3 cross 3 matrix, and it is being multiplied by a 3 cross 1, and that will give me a 3 cross 1 matrix. So my K can be a 3 cross 3 matrix. Okay. And also it cannot be a constant. I mean, it cannot be only a number. This K cannot be only a number, and that I will show you. Okay. So this is actually not correct mathematically. So first of all, my heat flux vector is it. So I am not writing the, okay, let me write it like this. So, or let me write it, Qx double bar Ex cap Ey cap and this is Ez cap. Okay, correct. So I have seen that mathematically I have two options, that is this k can be a constant and this k is a 3 into 3 matrix. So let us see that where these two cases can happen. Okay. So in general, see, my heat flux vector is written like this, and you should be now acquainted with this nomenclature. This one is Q3. Okay. And I can also, okay, now from this step I should take a different approach. Now I have told you that my Q1 is a function of temperature gradient, but it has three options. So my Q1 double prime can be a function of del Tx or del T1, that is the component of the temperature gradient in x direction, or E1, or in the direction of E1 unit vector. So let me write the temperature gradient also, then it will be clearer. Okay. Okay. So what I am telling is that this component of heat flux vector, it can be a function of this one and this one. This component of heat flux vector, it can be a function of this one and this one. Similarly, this component of heat flux vector can be a function of this one, del T2 or del T3, right? So according to that, I will have, so let me write it with this color. Q1 double dash is equal to A11 into del T1 plus, or let me write K. So K12 del T2 plus K13 del T3, then my Q double prime 2 will be K21 del T1 plus K22 del T2 plus K23 del T3, and my K double prime 3 will be again K31 del T1 plus K32 del T2 plus K33 del T3. Okay. So it is the same way that, so this K was only a constant of proportionality between this temperature gradient and this heat flux component. Okay. So these are nothing but nothing but those constants. So this constant is correlating my Q1 double prime and this del T1. I am sorry. Similarly, this Q23 is correlating my Q2 double prime and this del T3. Okay, and my Q3 double prime is correlated with this del T2 is by K32. So like this. Now I can write these three equations in matrix form. So that will be Q1 double prime, Q2 double prime, Q3 double prime is equal to K11, K12, K13. Okay, and this one. So this will be delta T1, delta T2 and delta T3. Fine. So now this is the general case. In Fourier's law of heat conduction, nowhere it has been told that this Q1 is only a function of del T1. Nowhere it has been told. So in this kind of experiments, what we actually do is to deal with only one direction, we insulate these directions. Okay, so that there are no heat transfer in the transverse directions. So heat transfer is only allowed in this direction. Maybe this is x. Okay, but it is nowhere being told that my Q1 is only a function of del T1, Q2 is only a function of del T2 and so on. Okay. So now I can write this as, for the sake of completeness, this is a Q matrix or Q double dash matrix, or it is a vector, it is a column vector or column matrix, and this is a K matrix, 3 cross 3 matrix, and this is another column vector delta T. Okay, and you see that this is my 3 cross 1, this is 3 cross 3, this is again 3 cross 1. Okay, so this is the Fourier's law of heat conduction in three dimension. Okay, Fourier's law of heat conduction in 3 dimension. Okay. Now the next step is to show that if the material is isotropic, then this is a identity matrix, or I can say that this is equal to K 1 0 0 0 1 0 0 0 1. Okay, and then we can show that for an isotropic material this is equal to K grad T of 1. Okay, and this is equal to K grad T2, and this is equal to K grad T3, sorry. So that is, if I have this vector here, grad T vector having 3 components like this, if I multiply only by a scalar, then I can get this one. But this is true what I am doing. So this is true only for this condition that the material is isotropic. Okay. So to prove that, I need to teach you some tensor calculus. Okay. So, and that I will do in the next lecture, because I have already taken so much of time during deriving the thermal energy balance by the second approach. Now you might be thinking that why I am doing so much of these things. Okay, because you already have studied the heat transfer in this form, only in this form. But believe me, in the practical case, you can have some cases where the isotropicity is not there, where there is a considerable anisotropicity in the material. Then you might have to modify your Fourier's law of heat conduction, that you have studied in your UG thing. Okay. And also, if even you, I mean, even if you are having a totally isotropic situation, then also all these things will not go in vain, because see, tensor calculus is something that will be surely needed if you are a mechanical engineer. So tensor calculus has its application in strength of materials, in advanced strength of materials, because in our UG level strength of materials also we don't need actually this tensor algebra or tensor calculus, but in M.Tech level or in MS level mechanical design courses, you will have some courses like applied elasticity or applied or advanced mechanics of solids. So in those courses you have to know the tensor algebra, otherwise you will not be able to proceed. And if you go through some advanced level fluid mechanics or heat transfer books, there also they have taken the help of the tensor algebra. Actually tensor algebra reduces the complexity of those expressions. Okay, and that I will show you in the next lecture. That is, the dealing with tensor algebra is much easier, and it is much efficient from the time point of view also. Okay, you can write much bigger expressions in only one line, or maybe in or maybe with the help of some 2 or 3 letters. Okay, so that is the power of the tensor algebra or tensor calculus. So in the next lecture I will teach you the tensor algebra. Okay, and then I will prove you the that the if the material is isotropic, then only my this K matrix, this thermal conductivity matrix, boils down to this uh, constant K into an identity matrix. Okay. So until then, uh, we will call it a day, and if you have any doubt, uh, you must write that in the comment section. And also, if you feel that I am going faster, or if you feel that I am going very slow, or if you feel that why I am teaching all these things, I mean, if any part of the course you feel that it is not necessary, I mean, what is the purpose behind teaching this thing, you can write that in the comment box. That is why I am studying that tensor calculus here. That, I mean, that I have explained already, but still, if you have anything in your mind like that. Okay, so goodbye and take care. Thank you.